Hello, welcome to a review on work energy and simple machines. Very important problem that will help you on your test for this unit. Clyde, a stubborn 2,000 Newton mule, refuses to walk into a barn. So Farmer McDonald must drag him up a 5-meter ramp to his stall, which stands zero point 0.5 meters above ground level. Farmer McDonald needs to exert a 500 Newton force on the mule to drag him up the ramp with a constant speed. A, what is the input force? B, what is the output force? What is the input distance? What is the output distance? Those are all given in the problem. A through D is given in the problem. And then we're going to calculate the AMA, the IMA, the output work, the real input work, the ideal input work, the force of friction, how much energy, how much of the farmer's energy is wasted, and what is the efficiency of the ramp. Have a pad and paper, a pencil and a pad, a pencil and a pad of paper with you so that you can follow along. A calculator will help you. And see if you can predict where I'm going with this. Maybe you want to turn the video off or put it on pause and try the problem yourself before you look at the problem. So let's begin by identifying what's given and what those values are. Clyde, a stubborn 2,000 Newton mule, that's going to be the FW or the weight, refuses to walk into a barn, so Farmer McDonald must drag him up a 5-meter ramp. In other words, it's 5 meters long, the ramp. The surface is 5 meters long. To a stall, which stands 0.5 meters above the ground, so that's the height of the ramp, or the DO. It's above the ground. Farmer McDonald needs to exert 500 Newton force on the mule to drag him up the ramp with a constant speed. So that's going to be the applied force. Farmer McDonald is going to apply a force of 500 newtons to a weight of 2,000 newtons. A distance of 5 meters is DI, and that's going to end up 0.5 meters off the ground or above where you started, which is DO. Now, the input force is 500 newtons because the input force is the same as the applied force. Input force is the same as the applied force. So that's 500 newtons. What is the output force? Well, the output force equals the weight of the load, and that's going to be a 2,000 Newton mule. So that's the weight of the mule. The input distance is the length of the ramp, which is 5 meters. What is the output distance? That's going to be the distance you end up above the ground. So that's going to be 0.5 meters. Now let's begin to examine the problem. Now we've identified A through D, so let's start with E. And in this case, we're going to do E and F together, AMA and IMA. Usually the AMA and IMA are done at the end of the problem, but in this particular problem, it can be done early because the output force, input distance, and output distance are all given in the problem. And the AMA is the output force divided by the input force. So it's 2,000 newtons divided by 500 newtons. Newtons cancel, and I'm left with 4 as the IMA, which has no unit labels. The ideal mechanical advantage is DI over DO, which is 5 meters divided by 0.5 meters. Meters cancel. I'm left with 10. So, the difference is dramatic between the output force and the input force. So let's look at the problem a little more closely and see why the difference in AMA and IMA is so great. See if we can explain that. Well, the output work is what the input work should be if it were a clean or an efficient machine. And that's going to be 2,000 newtons times 0.5 meters. Output force times output distance, which is 1,000 joules. The real input work will be 500 newtons times 5 meters, which will equal 2,500 joules. What is the ideal input work? Well, the ideal work input is always equal to the work output. So it's going to be 1,000 joules. So G is 1,000 joules, H is 2,500 joules, and I is the same as G, or 1,000 joules. So let's look at J, which is probably the most important calculation because that's what separates the ideal from the real machines. In order to calculate the frictional force, we have to calculate the ideal force first. I set the equation, or the ideal machine equation. I rearrange it and set it equal to Fi, F output times distance output divided by distance input is going to be 2,000 newtons times 0.5 meters. 2,000 newtons times 0.5 meters divided by 5 meters, and that's going to be 200 newtons. So that's what it should take. The farmer, it should take 200 newtons. That should be the applied force. Well, the applied force is not 200 newtons, it's 500 newtons. So the amount of friction should actually be kind of obvious right now. Energy is neither created nor destroyed, but it can be transformed from one to another. Well, how much of that work is due to, how much of that wasted work is due to friction? Well, the frictional force will be 500 newtons, the applied force, minus 200 newtons, the ideal input force, will be friction of 300 newtons. So when I calculate, I say, what is the heat? What is the heat? What is the work that's converted to heat? Well, it's going to involve the frictional force and the input distance. So let's calculate that. Let's calculate how much of the farmer's energy is wasted, or in other words, how much of the work is converted to heat. So when you have wasted work, that's the same as heat, usually. In other words, work is neither created nor destroyed, it can be transformed. So how much of that applied force, how much of that real work input is actually due to heat? Well, it would be the force of friction times the distance, or 300 newtons times 5 meters, which will equal the work due to friction, or 1,500 joules. So the work due to friction is 1,500 joules. And what is the relationship between the work due to friction and the wasted energy? The farmer wastes. Well, it's going to be the same. It's going to be equal. The wasted work is going to equal the work due to friction, which is 1,500 joules. So when you say how much of the farmer's energy is wasted, it's going to be 1,500 joules, and that's going to be the same as the work due to friction. So I hope you see the connection between work wasted, work friction, etc. Now, let's look at the efficiency. The efficiency, you can calculate it by either saying AMA over IMA, or the output work divided by the input work. The efficiency is going to be equal to 4 over 10, or 1,000 over 2,500. 4 divided by 10 is 0.4, and 1,000 divided by 2,500 joules. 1,000 joules over 2,500 joules is going to be 0.4 as well. Joules cancel. Efficiency can equal AMA over IMA, or work output over work input. Efficiency has no unit labels. It has no unit labels. Well, that concludes this particular problem. I hope you do well on your test on this unit, on work energy and simple machines, and take care.